So welcome everyone for the second weekly live session for the course Geomorphic Processes, Landforms and Landscape. It is taken by Professor Javedan Malik on the NPTEL platform, and myself Ananya P. Mukherjee. I am a PMRF Fellow from the Department of Earth Sciences in IIT Kanpur. So this session is going to be kind of like a summary of your entire week's content, and also this will help you in getting sorry, 1 minute, I'll just admit people. Okay, so this will also help you in trying to solve the weekly assignments that are given to you. Okay, so this is a live session. You are free to interact with me. You can post your doubts during the session in the chat box, or you can raise your hand and ask. Any kind of interaction is open over here. And also I will just put some of the details where you can you know access the recorded lectures as well as the slides. Okay, so I am putting the links. So the recorded lectures will be published on YouTube. Okay, so it is my channel. You can find it under the playlist as per the course name itself. Okay, so you can find it over there. It will be uploaded either like by tonight or latest by tomorrow morning. Okay, so in case you all want to refer back to the lectures, refer back to the the sources that I am, the slides that I will be showing, you can access them from the links that I have mentioned in the chat box. Okay, so that's a brief introduction, and thank you for joining. So we will start now. So as we had discussed in the previous session, we were discussing about an introduction to what is geomorphology, what are the different sections that we will be studying in geomorphology, and what it means, what are we going to study, and what are the different processes and agents that are kind of shaping the landforms, landscapes that we see on the Earth's surface. So over here, you can see that one of the most important, kind of processes are these endogenic processes. Okay, so endogenic has two kinds of movements: slow and sudden movements. Both the movements that are mentioned over here, okay, so the driving forces for these the two movements is actually from the interior of the earth. These are not mostly not caused by the agents acting on top of the earth's surface, but they are actually driven by the processes that are acting below the earth's surfaces. Okay, so that is why actually they are called endogenic. So in today's live session, we are going to learn about the different kind of processes that are driving these changing mechanisms that is kind of building up or destroying the earth's surface in the present day and also in the past. Okay, so moving on, first we will discuss about the earth's interior. Okay, so earth's interior, as we know currently in the present day, that it is a layered kind of a structure. Okay, so the earth is made up of different layers which can be classified or categorized like on the basis of two ways. One is mechanically and chemically. Mechanically means the physical properties of each layer is different. Okay, rheologically that we mean. Then that means that they are at different states of matter. Okay, so we don't find any particular layer in the gaseous form, but gases are trapped, okay, even within the earth. but mostly the two states of matter that we find is the solid and the liquid. So according to that, we have the lithosphere, we have the asthenosphere, we have the mantle, we have the outer core, and we have the inner core. Okay, so these are the layers that are distinguished on the basis of their mechanical properties. Then moving on to the chemical or on the basis of the composition of the layers. Okay, so we can have excuse me. So on the basis of that, we have the crust, okay. Then we have the mantle, which is again divided into different upper and lower mantle based on the kind of the composition, the chemical composition that is present, okay. And then you have the outer core, and then you have the inner core. Now obviously the mechanical classification, mechanical categorization and the chemical categorization, they are overlapping, okay. So that means that their chemical composition is related to the mechanical properties that they have, and vice versa. So they are interrelated. So this is an introduction, the basic of what we deem as the representation of the Earth's interior. Okay, different layers, crust, like basically crust, mantle, core. Okay, so these are the three important layers that we consider when we are talking about the Earth as a whole. So next, obviously the transition between these layers is not a continuous or gradual transition, okay. You will find that in between the consecutive layers there is a zone where you find a drastic change in the properties, either the mechanical properties or the chemical properties. Okay, so you have different kinds of discontinuities within the Earth's interior. Okay, so you have the Conrad discontinuity, so that is between the upper and the lower crust. Okay, so we will learn a bit in detail in the coming slides. Then you have the Mohorovičić discontinuity, or in short we call it as MOHO. Okay, so which separates the crust from the mantle. Okay, so this is one of the main kind of discontinuities when we are consider about most of the the mechanisms or the processes that we deal with while we are considering the continental building and the destruction of the different plates. Okay, then you have the repeated discontinuity. This is the discontinuity which is kind of separating the upper from the lower mantle. Then you have the Gutenberg, which is between the mantle and the outer core, and then you have the Lehman discontinuity, which separates the inner and the outer core. Okay, so these are the different zones of distinction, okay, between the different layers. Now we learnt that the earth is made up of different layers. Okay, we right now our technology is not that developed, where we kind of can drill all the way till the center of the earth, okay, and understand the layered structure. So how did we come to know of this layered structure in the earth's interior? Okay, so there are different sources which we use for gaining knowledge about the earth's interior. So you can have direct sources and you could have indirect sources. Okay, so what are direct sources? Direct sources are actual physical evidences that we get. Okay, so you could get those evidences from, say, surface rock or volcanoes, obviously mining and drilling areas. And we have it's a very well known project that we have, that is deep ocean drilling project, and you have integrated ocean drilling project. Okay, so these are the sources where we can get physical samples, physical information about the structure of the earth's interior. Okay, But the limitation of direct sources is obviously the depth. We cannot go to deeper than a certain depth because of the limitations of our technology itself, technology and also instruments. So what we base our knowledge about the Earth's interior, it's from the indirect sources. Okay, so what are the indirect sources? Indirect sources are measurement of physical properties of the Earth's interior, okay, that we take on the surface. We will physically not go to the depth, but we will try to kind of measure the different physical properties using different techniques. Okay, so you have the temperature and pressure variations, you can have seismic waves and you know how they are traveling and the travel time information from seismic waves. Okay, then you have meteorites, we find samples of meteorites, we try to understand their composition, we try to date them, so we and compare those information from what we know about the Earth's composition and Earth's age. Then we have gravitation and magnetic field. So gravity, the changes in the the acceleration due to gravity at certain points, and the magnetic field also, we measure magnetic field and we try to understand how the variation is differing from one place to the another. Using these information, we the current image that you see over here, this Earth's interior, is mostly based on indirect sources and some amount with the direct sources. Okay. Now these are the some like the seismic waves, okay, are the best till date the best way to get information about the Earth's interior. Why? Because during an earthquake event, okay, there are different kinds of waves that are generated. Okay, so the most common ones or the primary waves that are there, that is P waves, and you have shear waves. Okay, how these travel from one point on the surface of the earth to the other point on the surface of the earth can give us the understanding about how the earth's interior is layered. Okay, because as a property of the waves, a wave can get reflected from a surface or it can refract through a medium, then again traverse through that medium and then get again refracted out, and you can gather that you can kind of observe that wave. Okay, so using seismic waves, most of the the Earth's interior has been uh, schematically representative. Okay, so seismic waves are one of the most important indirect sources of information about the Earth's interior. So that is where the the discontinuities that we spoke about comes in play. Okay, so when these seismic waves are traveling through the Earth, they will either get reflected from these these surfaces, these discontinuities, or they will pass through the discontinuity in the consecutive medium and they will travel through that, and then based on the other discontinuities that are present, they might interact. In the left hand side, you can see a preliminary Earth reference model, okay, PREM model. So in this you can see that with depth, the velocity of these seismic waves have been plotted. Okay, so you can see that compared to the crust over here, the velocity is much higher in the core, the inner core. Okay, and you can see that there are these sudden jumps, at the areas where the discontinuities are present. Okay, you can see all the areas where there is a sudden jump. So this is how seismic waves can help you to understand. It has helped the researchers understand that there are zones where the mechanical or the chemical properties are changing within the Earth's surface, and that is why we have got this Earth's layered interior structure. Okay, in this diagram over here, in the seismic discontinuity, you can see the different discontinuities and where they are present. Okay. And this chemical composition chart shows us that most of the the earth's surface, or the earth as a whole, the maximum amount is given by iron and oxygen. Okay. Why iron and oxygen? Because oxygen mostly combines with the other elements and it forms the oxides. Okay. And earth's core in itself, as we will see in the coming slides, that earth's core is essentially made up of the iron and nickel. Okay. So that is why this diagram will give you an approximate kind of percentage amount of the different elements that are present in the earth as a whole. So next we move to the earth's crust. Okay, so in detail you can see even over here that oxygen is the most abundant, okay, over here, and then you can see the silicon, the silica for that matter. Okay, silica is SiO2. Okay, this is one of the most abundant kind of oxide that is present on earth's crust. Okay, and the elements that you can see is oxygen and silicon. Okay, so what we know about the crust, it is the outermost solid part, it is a thin layer, but the thickness of the earth's crust varies from the continental part to the oceanic part. Okay, so the continental crust is much thicker. Okay, that is, it can go up to 70 kilometer, while oceanic crust is around 5 to 30 kilometer thick. Okay, and the what we say as the total thickness normally between 30 to 50, it's the average. Okay, average across the entire earth, that would be 30 to 50 kilometer of the entire crustal layer. Okay, then as per the knowledge of how temperature is varying with depth, we see that with depth the temperature rises within the crust. Okay, now the crust is mostly made up of the rocks that we study in geology and in earth sciences also. So mostly these rocks are sedimentary or igneous or metamorphic, but mostly the earth's crust is made up of sedimentary rocks. Okay, and the distinction between the continental crust and the oceanic crust comes uh, because of their chemical composition. Okay, so how are their chemical composition differing? So the chemical composition is differing, that the continental crust is mostly made up of lighter silicates. What do you mean by lighter silicates? They are less dense. Okay, and we call it as Cl, so that means it has more of silica and aluminium. Okay, and the continental crust is said to be made up of heavier silicates and it is denser. Okay, heavier silicates means denser minerals or denser silicates, and mostly that consists of silica and magnesium, which is known as SEMA. Okay, so that is why the Cl is mostly your continental and SEMA is mostly your oceanic crust. Okay, so that is why we see that the continental crust is thicker but it is lighter, oceanic crust is thinner but it is denser. Okay, we will understand the effects of these density variations when we come to plate tectonics and we see how it's kind of affecting the plate movements. Okay, the movements of the tectonic plates. Then now we know that crust is distinguished on the base of the chemical composition of it. Okay. Now if we speak about the mechanical categorization of the earth's interior, crust is part of the lithosphere. What is lithosphere? It is the earth's rigid outer layer, okay, but along with the crust, the lithosphere also contains some part of the upper mantle, okay. So it is essentially a rigid or the solid part of the earth's layer, of the earth's outer layer, but it also consists some part of the upper mantle, okay. So your lithosphere is actually the crust plus upper mantle, okay. Then you have something called asthenosphere. Asthenosphere is just below the lithosphere, okay, and the lithosphere kind of flows on top of the asthenosphere, okay. Why? Because asthenosphere by its mechanical nature is actually soft and plastic, okay. So asthenosphere is also present on the upper zones of the mantle, okay, but below the lithosphere. So these are the two essential layers that we need to consider when we are talking about the later on or in plate tectonics, or the way that the earth's lithosphere breaks apart or they are joined together at places. Then we move to earth's mantle, okay. So the mantle is kind of the most of the yes, Pravesh, you have a question?
Yes, ma'am.
Yes,
Ma'am, why asthenosphere is partially melted?
sorry.
Ma'am, why asthenosphere is partially melted?
Partially melted. See, the thing is that with as we had mentioned before, all with depth the temperature increases. Okay, and with temperature also there are pressure variations that we see. Okay, because of that, it is kind of it's partially melted, and it's because of that property only that the lithosphere is kind of floating on top of asthenosphere. It is also due to the presence of some amount of water in the the chemical composition of asthenosphere. Okay, there are fluids like water in molecular form. Okay, water in molecular form is present along with the other elements and other chemical composition that is making up the asthenosphere. That is why, because of that, it is liquid, it is like partially molten, and also uh, uh, as I said that with with the depth the temperature also increases. So higher the temperature, obviously, as we know that the solids kind of zone into the liquid state. Is that clear?
Yes, ma'am.
Okay. So the Earth's mantle is kind of it comprises of most of the the Earth's interior, the most of the area, if you can say, of the volume. Sorry, the volume of the Earth's interior. So it goes on from the 35 kilometer up to 2,900 kilometer. 35 kilometer, if you remember, is the Moho discontinuity. Okay, and the discontinuity that is present at 2,900 kilometer is your Gutenberg. Okay, so as we said before that mantle is divided into upper mantle and then you have the lower mantle. Okay, so that mantle is also divided into two. Because why is it divided into two? It's because of the difference in their densities. Okay, we can see that the upper mantle has a lower density and the lower mantle has a higher density. Also, the layering of the Earth's interior, okay, it gives us a very direct indication of the different densities and the density variation that is present within the Earth's interior. Okay, so the solid state, yeah. So mostly lower mantle is said to be in a solid state, but it is not essentially solid because it is not fully solid, as I said even before, that chemical composition below the within the earth also has water in its molecular formula. Okay, so lower mantle is it's mostly in that partially molten also, okay, but it is more towards the solid state. Okay, so then again with depth the temperature increases and it can go all the way up to 4000 degrees Celsius at the core mantle boundary, that is your Gutenberg discontinuity. Okay, why is it important for us to understand about the Earth's mantle? Because most of the mechanism that we see, okay, of the plate tectonics or the what we call as the convection cells that we see is happening in the mantle. So mantle and the convection cells in the mantle is actually responsible for the lithospheric plates that are moving on the earth's the lithospheric plates of the earth's crust. Okay, we will study this in detail in the coming slides again. So but it's important for us to know about the earth's mantle, how it is layered, and mostly its relation kind of to the asthenosphere, and it is important to know that of its position just below the lithosphere. Okay, so mantle is where the driving forces actually occur. Then you have the earth's core. Okay, so the core is actually the heaviest kind of layer in the earth's interior. Okay, as I even mentioned before that most of the core is actually made up of nickel and iron. Okay, so these are actually most of the heaviest material that you will find, and uh, even in core you have two kind of layer distinction. One is the outer core and the other one is the inner core. Okay, now the density of core, as I mentioned before, the density increases when we move towards the center of the earth. You can see over here that the value ranges from 5.5 to 13.6 grams per cc. So it's the densest layer within the earth's interior. Okay, now the outer core, the main kind of a distinction between the outer core and the inner core is the state they are in. The outer core is a liquid, okay, but it is not under enough pressure to solidify, but the inner core is a solid. Okay, so actually the kind of the heat that is required for the outer core to stay in the liquid form is actually given by the radioactive decay that is happening because of the cooling of the earth's inner core. Okay, this is one of the main reasons why the outer core of the earth is actually in the liquid form and the inner core is actually solidifying. It is cooling slowly and it is forming into a solid. It has been happening since the time of the earth's formation. Okay, so the heat that is generated due to the radioactive decay due to the cooling of the earth's inner core is actually keeping the earth's core in the liquid state, and that is actually one of the kind of driving forces or the hypothesis that we have for the earth acting like a geodynamo and generating its own magnetic field. Okay, so this is one of the important things that we need to know. And there is another fact that the rotation of earth's inner core is slightly quicker than the rotation of the on the surface. Okay, and in the inner core there is not a persistent magnetic field. The magnetic field is actually due to the presence of the inner core and the convection that is happening due to the presence of the liquid outer core and the the convection that is happening in the outer core. Okay, so that is why the earth's core is important in that sense, that it is one of the factors that why we have the geodynamo effect. Now we learned about the Earth's interior, how it is layered, why the layers exist. Okay, uh, because of the Earth's layered structure, okay, a lot of processes that are happening within the Earth's surface has an impact on the on the processes that are happening on the Earth's crust, like on the Earth's surface. So we know right now that the continents that are in the present position, that was not where they were previously, like in the geological past. If you remember, in the last session we spoke that the earth is approximately 4.6 billion years old. Okay, so when we say 4.6 billion years old, obviously we know that the present position of India is not where it was, like say a few million years ago. Okay, so how did we this how do the land masses move on the earth? Okay, so a lot of researchers found evidence of the fact that once all the land masses, all the continents that are existing in the present day, they were kind of joined together. Okay, so you can see that the timeline of the whole plate tectonics theory started as early as 1910s, 1905. Okay, so you can see that by the early 20th century, uh, the scientific opinion that was that the earth had cooled from its original state of being a molten body. Okay, and the contraction resulted in the density differences that we find in the different layers. That's why the denser material, that is the earth's core, is in the middle. Then you have the slightly higher denser mantle, and then you have the lighter crust. Okay, so this was established in the early 20th century. Okay, now the earth's crust that is there, okay, so because of this resultant cooling of the earth from the molten state, they said that the mountain ranges and the ocean basins were formed. While they were right about how the earth cooled from the molten state, they were not correct about the whole mechanism of the mountain ranges and the ocean basins forming. So in 1915, a very well known name you must have heard is Alfred Wegener. Okay, he proposed the continental drift theory. According to this theory, he said that the continents drifted relative to each other in the past, okay, and that's how they came into the current position. While it was one of the breakthroughs in the entire, understanding the Earth's history, okay, it really helped us in understanding, or kind of opening our eyes towards the fact that the earth is not a stationary system, it is moving. The earth's crust is breaking apart and joining at places. Okay, so this the continental drift theory is the start of these concepts. Okay, but he could not explain the mechanisms that were driving these continents to move across the earth's surface. Okay, so it was kind of disproved later on, okay, because of the limitations that was there, because he could not explain the mechanism properly. So in 1950, uh, work was happening based understanding the magnetic field and the magnetism that is found in the rocks that are found on the continents. Okay, that led to kind of also researching or trying to understand whether the how the magnetism patterns are found, or magnetism is occurring in the ocean floor. Okay, that's the time people started researching on mid oceanic ridges. Okay, so mid oceanic ridges gave the idea about the whole sea floor spreading. Okay, it also explained that the magnetism that was there, it forms a repetitive pattern along the mid-oceanic ridges that were found. They were actually described as the mountains that are being found on the ocean floor. Okay, so these were the discoveries that were being made, and when they mapped the entire, that mid-Atlantic Ocean ridge, that's where they realized, later on they realized that what Wegener was saying, that the continents were actually together at one place at one time and then they drifted apart. They were slowly finding the, kind of validation for that theory. Okay. Then in 1962, Harry H. Hess, he gave the entire process about the sea floor spreading, which is related to the mid-oceanic ridges forming. Okay, so he said that at the mid-oceanic ridges, the Earth's crust is breaking apart, but new mantle material is rising on top and it is building the Earth's crust. Okay, so this was the basis of the plate tectonics theory that came after the continental drift theory. So the main difference between plate tectonics and the continental drift theories are that the continents are not thought of being just, cutting across the oceanic crust. Okay, that the continental drift theory was kind of giving uh, the assumption that the continents was cutting was, just kind of moving through the oceanic rocks, but that is not what the plate tectonics theory said. The plate tectonics theory said that the oceanic and the continental crust is actually moving over a layer, or a kind of like, kind of it is flowing on top of a layer which is partially molten or molten. Okay, so this is where the plate tectonics theory started gaining momentum. Okay, so a gist about the continental drift theory. Continental drift theory is still important even though it was disapproved later on by the researchers, is that it gave us the idea that actually the continents that are present today, the edges, the margins of these continents are actually, they fit together very well if you get them all together. Okay, so the whole ideas about supercontinent, continental breakup, continental assembly can be understood by the continental drift theory that was given. Okay, you can see that there are continuities of bigger geological features like fold mountains, then the presence of certain kinds of rocks and fossils. When you date them together, they fall in the same, kind of geological time. So that was another evidence that supported continental drift theory. Okay, and also paleobiogeographic and paleoclimatological records that are, that were taken by researchers later on, they also kind of gave the verification of this continental drift theory. Okay, so this is a short about the continental drift theory. It is important for us to know because it is one of the driving hypothesis or the driving principle on which the plate tectonics theory was based on. Next we come to the very important, aspect, that is the geological time scale. Now you can see over here that you have different eons, eras, periods and epochs. Okay, so this is of largest period. Okay, then it is divided into eras, periods and epochs. Okay, so most of the important kind of, transitions between the different epochs or different periods are actually based on the fossils that are found. Okay, so based on the fossils that are found, uh, the periods have been named, the epochs have been named. We don't have to get into the detail about the whole geological time scale. It is important for us to know some of the important names, that is, say, Proterozoic, then Archean. These are, the eons. Okay. No problem, Kuldeep. It's okay. You can now see the entire session. Okay. So then you have the Paleozoic era, Mesozoic era, Cenozoic era. Okay, so these are important for us to know because when we will be learning about the how the continents were at one time and how when the breakups happened, you kind of relate it to the geological time scale for understanding that how long ago these things happened and how long it has taken from that stage to the present stage. Okay, the figure on your right hand side is kind of like an two kind of a cartoon about the different fossils that were present. Okay, over here you can see there are P and T written. This is actually the Permian Triassic boundary. Okay, this is one of the most important times. There was a mass extinction during this time, and also the most probably the most well known is the KT boundary, that is when the dinosaurs went extinct. This was again a mass extinction period, the mass extinction event. Okay, so that is why we need to have a basic idea about the geological time scale. Okay, so you might have to remember few of the years and few of the events that happened. Okay. Then okay, so now we learned that plate tectonic theory came into picture. We spoke about the continental drift theory. Now, just talking about it and seeing that okay, they were fitting, that was okay. Researchers understood, but later on, researchers tried to reconstruct how the continents might have been, situated together during the different in the geological past. Okay, so in the first diagram over here, you can see that they said that there was a one big supercontinent. Okay, supercontinent is the assemblies of all different continents. Okay, when I say supercontinent, it's a big continent. It comprises of the present day continents also. Their names might have been different in the past. Okay, so that nomenclature happens as per the researcher. So some 600 million years ago. Now 600 million years ago means it is in the Proterozoic era. Okay, that was the oldest, kind of the older ones. Okay, that time there was no life. Okay, no life on earth. Remember this, that the oldest, like before 541 million years ago, there was unicellular life, there was no multicellular life. Okay, so around 600 million years you had a big supercontinent called Rodinia. Okay, and there was a big ocean. That's it. Okay, and the Rodinia, kind of you can see where the present day continents are situated in Rodinia itself. You have China, Congo, South America, Siberia, then you have Australia. Okay, this is how the present day continents were situated in the entire of the Rodinia supercontinent. Okay, then at 500 million years, some part of this Pannonia kind of drifted apart. Okay, okay, so you can see that the Pannonia drifted and some part like Siberia started drifting northwards. Laurentia also drifted northwards. They were breaking up, away from the big continent. Okay, then at around 300, Laurentia collided with Baltica. That is where we found the Appalachian Mountains. Okay, that is on the eastern side of the North America. Okay, due to the collision between the Laurentia landmass and the Baltica landmass. Okay, you can see over here. Then around 200 million years ago, during the time when dinosaurs were there, okay, the supercontinent was known as the Pangaea and it was surrounded by an ocean called the Panthalassa. Okay, so you have the Pangaea and then Panthalassic, or the Panthalassa ocean, which is kind of the the starting point of the present day Pacific Ocean. So that was around 200 million years, where all the continents, the current continents, they were all joined together to form the big continent called Pangaea. Pangea, we've heard about it a lot, even before. Okay, then around 100 million years ago, the Pangea, that the supercontinent Pangea, started breaking apart. Okay, it broke apart and it gave rise to what we call the Atlantic Ocean, Pacific Ocean, and there was another ocean, that is the Tethys Ocean. Okay, Tethys Ocean is important for us to know because it plays a part in the entire Himalayan orogeny. Okay, I'll get back to the Aravalli mountain ranges, okay, in a slide later on. So, around 100 million years ago, you have the Tethys Ocean, you have Pacific Ocean and Atlantic Ocean. All these oceans were created because Pangea was breaking apart, the land masses were breaking apart. Okay, 50 million years ago, again, few of the continental fragments, they kind of, pushed up together, they were colliding together, and that gave rise to some of the most important mountain ranges like, the Alps in the Europe, and then you have Himalaya because of the collision between the Eurasian plate and the Indian plate. You can see that around 200 million years ago, India was part of the Pangea. Okay. Then at around 100 million years ago, you see that the India broke apart, okay, from the Antarctica and the Australia landmass. Then around 50 million years, you see that the India was traveling towards the Eurasian plate. Okay, so this is why it was important for us to understand the plate tectonics theory, how the continents were actually drifting apart. Okay, so this is just a schematic. This was reconstructed by researchers based on geological evidences. Okay, like as I have mentioned before, you have paleomagnetic records, you have fossil records, you have the petrological records, that is the rock records. Okay, you date the rocks and you understand. Uh, uh, like for an example, some rocks that are found in India are also found in Antarctica, and they have been dated, and the time that they have formed is similar. So that means that they were together. Okay, so taking these information, these kind of supercontinental arrangements have been reconstructed. So this is the present day scenario. Okay, so you can see that the there is an isthmus that is connecting between the North America and South America with the Indian plate, Indian landmass colliding with the Eurasian plate. The Tethys Ocean that was present before, that closed up. Okay, so that is one of the important events that happened, and because of this present, you know this has been in place for more than 50 million years. Okay, so around 40-50 million years. Okay, this is the present scenario. As you know that the recent earthquakes that have happened. Okay, so the earthquakes that are happening in the present time, earthquakes, volcanoes, okay, these are indicators that the plates are still moving. The plates have not stopped moving. Okay, they are still moving, and soon we will see, soon, maybe obviously not during our timeline, but in future, okay, in the coming years, thousands maybe years, we will see that the present scenario will change. Okay, so this is the heart of the plate tectonics. Plate tectonics says that Earth is not stationary, Earth's surface is not stationary. Yes, Africa splitting is one of the one of the important present day scenario where new plate material or new plates are being created over there because of these plate tectonic processes. Okay, and these the plate tectonics that is happening, it is one of the drivers for the different climatic changes that we see. Okay, previously, yes, height of Himalaya rising, when the collision is still going on. Okay, so after some time, obviously, the entire Indian plate will be the part of Himalaya probably. Okay, So these things are happening right now. And also, as we saw that India was previously, in the southern hemisphere. So since we spoke before also, the northern hemisphere and the southern hemisphere, the seasons change, the climate changes. We spoke about the Milankovitch cycles. Okay, due to these, you can see that India might have experienced, a glacial period, okay, during its geological past. But right now it is in the northern hemisphere, so the climate has changed. It is falling in the tropical area. Okay, so plate tectonics is actually the most important process or the theory that has been put forward to understand most of the earth surface processes. Okay, so for geomorphology also, this is the base or the platform on which we study the other geomorphological processes. Okay, now one more principle which is very important for us to understand about the kind of the vertical processes that are happening as well as the horizontal processes that happen on the earth's surface, on the earth's crust, that is isostasy. Okay, so what is isostasy? It is the state in which the force of gravity pulling the plate towards earth's center is balanced by the resistance that the mantle gives to the plate, which does not let the plate sink. Okay, so we said that the continental plate is lighter. Okay, it is floating on top of the asthenosphere, the lithosphere if we talk about. Okay, but when we are talking about, say, mountains are building, well, the mountains are building, even though it is a lighter material, the amount of material is still increasing. So that would suggest that it should sink down, but that is not the case. Okay, so that is where your principle of isostasy uh, comes in play. Okay, so isostasy in terms of the whole earth surface, that means that the tectonic plates are floating on the mantle like a raft floats on water. Yes, Turkish earthquake is related to the plate tectonics also. I have a few slides, which is going to talk where I'm going to talk about the earthquake to try to make you understand how different kinds of plate boundaries are acting at that point where the earthquake took place, and I will also give you more examples, okay, which have happened in the past, like the tsunami and the earthquakes. Okay. So, isostasy is one of the principles because of which the entire the continental building it is driven by that. Then you have the oceanic crust being denser and why it is thinner than the continental crust, while both of them are a part of the crust. Okay, so we can see that the crust on its, like, in at an average it has, like, 2.6 grams per cc density, while the average density of the mantle could be around like 3.4 grams per cc. Okay, so as we know how it is working, the less dense material will be floating on the denser material. So, example, one of the most evident examples is the Himalayan route, the Himalayas. Okay, so how Himalayas come into the place? Okay, as I said before, that the material is, Himalayas are rising. Okay, so more and more material is coming over there. Okay, because of the collision, then the plates are still moving, so the material and it is rising. Okay, though the material is rising, okay, there needs to be equivalent amount of material underneath the Himalayas to support the weight of the Himalayas on top of the surface. Okay, that is where the entire roots, mountain roots come into the picture. Okay, you can see over here, okay, more the height above the sea level, okay, deeper are the roots that are present. Okay, this the material present below the sea level is called the root. Okay, over here you can see, suppose this is a oceanic crust. Okay, so above the sea level there is a very less amount of oceanic crust that is above the sea level, and relatively you can see that the root of the oceanic crust is much shallower. Okay, so consider this as your mountain, and this continental or mountains for now, and this is a sea floor. Okay, so you can see that this is the difference between the roots. So this is the isostasy hypothesis. Okay, now you have two models, one is Pratt's model and the other is Airy's model. Okay, what Airy suggested is that all the blocks have equal density, but they have different thicknesses, and that is why they are floating at different depths. Okay, while Pratt's suggested that they all are floating at the same depth, okay, but they have different heights and different density. Okay, so these are the two different isostasy models that are kind of globally considered when we talk about isostasy and isostatic equilibrium. Okay, one of the most important examples of isostasy, which you can understand very easily how isostasy comes into place. Suppose that the mountain is building. Okay, as the material is coming adding on over here, so the roots will get deeper. Okay, so the roots it will start sinking also in a way so that it stays in an equilibrium. Okay, so it does not sink. So the entire, because of the weight of the material on top, it does not sink, the plate does not sink. Okay, but as we know, with time natural agents are working and the mountain starts eroding. When the mountain starts eroding on top of the sea level, the material is decreasing. Okay, so as the material decreases, okay, so the root tries to adjust to that to return to the equilibrium position. The root will start shallowing up. When it starts shallowing up, the mantle material or the asthenospheric material that is present, that will start flowing towards the root. Okay, you can see the arrows over here. When the root is sinking, the mantle material flows away from this place. When the root is it is rebounding, that we call crustal rebound. Okay, this is very much evident in glacier areas. Okay, when the glacial ice starts melting away, the weight that was there because of the glacial ice starts reducing, and the crust over there starts rebounding back, so that the root is actually shallowing up. Okay, and over there you see that the mantle material starts flowing towards the root. Okay, so this is one of the examples of isostasy. But ma'am, where it goes inside the mantle? Yes, those are the plate boundaries that we are going to talk about, where crustal material is going in the plate, in the mantle. Okay, right now we are only talking about how the continental plates, how the continental crust and the oceanic crust are floating on the mantle. Why isn't it sinking right now? Okay, like it is at an equilibrium. Okay, this is the whole principle of the isostasy, which says that all the continental blocks and the oceanic crustal blocks, they are actually at an equilibrium because of the principle of the isostasy. Okay. Now we come to the important part of the entire, like why we study the Earth's interior, why we studied the how the plate tectonics theory evolved. Okay, you can see over here these kind of different features that are marked. Okay, these are the different plate boundaries, and the plate boundaries between two plates, okay, can be of different types. The types are related to the relative movement between the two plates. Okay. So for plate tectonics, we can consider a plume model or a plate model. Okay, now plume model and plate model are kind of exactly similar, like the mechanism is similar, but it's just for plume model we are considering the mechanism to be a mantle plume. What is a mantle plume? Mantle plume is at a certain place. Okay, a molten mantle material is kind of floating on top. It is rising from the mantle and it is coming towards the crust and it domes upwards. Okay, that is a mantle plume. Now the driving force of mantle material rising on top, it happens in both plume model and plate model. Okay, to understand in a more schematic way, you can consider plume model, and to understand only the how the plates, how the crustal blocks are moving relative to each other, you can consider the plate model. For now we are only going to talk in terms of the plate model. Okay, so how the plates are moving, the crustal the lithospheric plates that are making up the earth's crust, how are they moving? When I spoke about the earth's mantle, I talked about the convection that happens. Okay, what is convection? Now somebody asked me where the material goes into the mantle. Okay, the convection cell is responsible, okay, for driving the lithospheric plates or part of lithospheric plates into the mantle at one place. Okay, so the crustal material over here, can you see? Okay, okay. So over here you can see that these are, suppose, the yellow, thin yellow lines that are there, these are the plates. Okay, so the plates are moving over here. You can see that the mantle convection, the direction is like this, then it is going down. So when it is going down, it is actually dragging this crustal material down. Okay, when it goes down, it is melting. Okay, it is melting, then it gets lighter in density. Okay, because it is melting, it has turned into liquid, now it is getting lighter compared to the outer core. Okay, so again it will start moving on top, because when something is lighter it will start moving on top from the denser medium. Okay, so this is the basic of how the mantle convection happens. Okay, uh, crustal material is dragged down into the mantle because of the convection current, then then the material starts melting, it is lighter than the rest of the earth's interior composition. So at another place, now this is where the mantle plume will rise. Okay, the mantle plume, with the mantle plume the material will again get transfer to the surface, to the crust. Okay, then over here you have the mid oceanic ridge. So the place where the crustal material is going down into the mantle is called the subduction zone, and where new mantle material is coming on top, which is forming the crust, okay, which is extending the crust, that is the mid oceanic ridge, mid ocean ridge. Okay, so the lithosphere takes part in the in going down to the mantle and then creation of the crust. Okay, the lithosphere is responsible, and the mantle is where the convection cells are giving it the kind of energy, it's giving it the direction of where to go and form or either get destructed. Okay, so over here these areas where you see triangles, okay, so these are subduction zones. Okay, over here this is the ridge. Okay, this area is the mid Atlantic Ocean ridge. Okay, over here you will see faults like this. Okay, so this is also another ridge area. Okay, so you can say the plates are getting built over here. Okay, then you have some dotted lines over here. These are the transform fault boundary. Okay, I'll come to the different types of plate boundaries. So this is in a whole what plate tectonics, how the plate tectonics are happening because of the convection currents that is existing in the mantle. Now we come to the different kinds of plate boundaries. Okay, so the plate boundaries, you have three. One is your divergent, you have convergent, and you have transform. Okay, so divergent is also called the convergent plate, it's also called the constructive plate boundary. Why constructive? Because that is where the earth's crust is building up, new crustal material is getting built up. Okay, so constructive. You have convergent. Okay, so you have convergent. Now convergent is also called a destructive plate boundary or collisional plate boundary. Why destructive? Because that is where lithospheric material is getting destroyed or it is getting dragged into the mantle. Okay, so that is where earth's crust is getting destroyed. So that is a convergent plate boundary. Then you have the transform plate boundary. Over here, neither new crustal material is being formed, nor any crustal material is getting destroyed. Over here, the plates just move past each other. Okay, either like later on you will learn about the right lateral and left lateral faults. Okay, so transform plate boundaries, the two plates are moving past each other. Okay, so these are the three basic plate boundaries that kind of comprise the entire plate tectonics, so that is happening on earth. Over here you can see that due to the different plate boundaries, you have different kinds of features that are seen on the earth's crust. Okay, so because of your divergent plate boundaries where the plates are moving away from each other. Okay, so this plate is moving this way, this plate is moving this way. Okay, so as the plates are moving away from each other, you can see that the mantle material can flow out on top of the earth's on the earth's crust. So that is where you get the ridge. Okay, the mid oceanic ridge that we talk about. Okay, so this is a feature that is formed due to the divergent plate boundary. When you talk about the convergent plate boundaries, the plates are moving towards each other. Okay, so because they are moving towards each other, one of the plates will move downwards below the other plate. Okay, so the plate that is moving over one plate, this is the overriding plate, and this is called the subducting plate. Okay, so this is your subducting plate and this is your overriding plate. Why? Because this plate is moving downwards, so this is getting subducted. Okay, this is actually a subduction zone. Okay, any a place where one plate is going below the other plate, it is called a subduction zone. This is the area where crustal material is going towards the mantle. Okay, somebody had asked me where is the place where the material goes to the mantle. Subduction zone is the area where the material is getting pulled into the mantle. Okay, and transform fault, as I said, that it will just form a big zone. Okay, like at the plate boundaries, at the margins of two plates. Okay, and you will find a broad zone where different other faults are also present. Okay, that is a transform fault boundary. There is like no crust is getting destroyed, no crust is new crust is coming up over there. So now this is a simple schematic representation of the different plate boundaries. Okay, so the first one, you can see that the plates are moving away from each other. Okay, so this is your divergent plate boundary. Over here is one plate is moving to the plates are moving towards each other. Okay, that to over here you can see this is the convergent plate boundary, okay, the destructive plate boundary. You can, the barbs are on the side of the overriding plate, okay. So actually this is overriding this. This is the subducting one and this is the overridden plate, okay. The triangles that are mentioned, that are shown, that is always on the overriding plate side, okay. And then you have the transform for boundaries, plate boundaries, that the the plates are moving along each other, okay, moving past each other. Now these are simple representations, okay. Now these can form in a combination. How in combination? Okay, so all the plates are right now situated next to each other, okay. So at one place the plates are going away from each other, okay. So suppose you consider only this plate, okay. So this plate is moving towards the right hand side and this is moving towards the left hand side, okay. So totally this plate is moving towards your right, okay. Now suppose there is another plate over here, say C, okay, say C. So between A and C, sorry, this is also A, okay. So this entire one is one plate, okay. So this is your entire plate and this is your B plate, okay. At some place there is a transform boundary also between A and B, okay. So like that you can have a combination of two plate boundaries or two kinds of plate boundaries between two plates itself. Over here you can see that this is probably a combination of all three plate boundaries, where this is your overriding plate, this is your subducting plate, this plate is moving that side, okay. And suppose there is this entire plate is there, okay. So this entire plate is moving this side. This plate will get consumed, this plate, this subducting plate will start getting consumed by the overriding plate, okay. So in that sense you have all these different kinds of, you will have these different combinations of plate boundaries, okay. Based on the different kind of plate boundaries and how they are forming, suppose there is a point where you have three plates, okay. Three plates can meet at one point. That point is called a triple junction, okay. Over here as it's mentioned also, triple junction is a name given to a point where three plates are meeting. Now three plates are meeting, all three might have different plate boundaries, okay. So then the triple junction that is forming is actually composed of different kinds of plate boundaries with different motions, okay, relative motion. So a triple junction can be stable as well as unstable. What is a stable triple junction? A stable triple junction is that which does not change with respect to the the motion of the plates. The triple junctions geometry does not change over time. What do you mean by the geometry? Suppose there are ridges, okay. Over here if I zoom in over here, you can see this is a triple junction, okay, between plate A, B and C, okay. Now since this is all a ridge, RRR means ridge, 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 triple junction, okay. So all these three are ridges, okay, and all of these are moving away from each other. Even after a certain time, this geometry or this orientation is going to remain the same. New crustal material is going to be keeping on build up, will keep on building up at this triple junction. So this is a stable triple junction, okay. Now if we consider one unstable one, over here you have a fault. FFF means transform fault boundaries, okay. All three plates have transform faults between them. Why is this unstable? Because as you see that this is moving like this is moving like this. So slowly this will start drifting away from these plates. Okay, so the fault will eventually turn probably into a ridge. Okay, so this is an unstable one. Now an unstable, a stable one will remain stable probably, or it may convert into an unstable one as soon as the geometry changes between the plate boundaries or the plate boundary types change. Okay, so these are kind of a combinations of different kind of geometries of triple junction. So when I give the slides to you, you can go through them and try to understand the geometries as per the simplistic diagrams that was given in the previous slide. Okay, so you can compare and you can understand how the plates are going to move relative to each other, and how this triple junction would look uh, at different settings. T means what? T means it's forming a T. Okay, suppose I consider this. Okay, this is plate B, this is plate A, and this is plate C. So this point is called the triple junction. That means that it is forming a T. Three plates are meeting at a point and they are forming a T. Now the T is a simplistic representation, it does not form a T, it is just to make you understand how three plates can meet at one point and form a T, and the point where all three of them are meeting is called a triple junction, because there are three plates that are meeting over there. Is that clear? I think Kuldeep asked the question. Okay. So this is a geological or like the real example of triple junctions. As I said, you can see that all these are moving away from each other. So this is a ocean opening, ocean opening, ocean opening. Okay, Africa splitting apart, somebody had mentioned previously in the chat. Okay, so this is a R R R. Okay, either rift or ridge, one of the convergent plate boundary features are being formed over here. So this is a stable triple junction. That means what? That Africa will keep splitting and new material will keep coming up over here, and this is the geometry that is going to stay even after a long while. Okay, so this is a stable triple junction. Over here you have the Macquarie triple junction, that is between the Antarctica plate, the Antarctic plate, the Pacific plate, and the Indo-Australia plate. Okay, over here you can see that this is an R, this is an R. Okay, and there is a T over here, and there is, sorry, this is a T. T means trench. I think that was what you were talking about, the T. Okay, R means ridge, that is the divergent plate boundary. T is a trench. Okay, so that is related to the convergent plate boundaries, and F is the fault, so that is a transform plate boundary. Okay, so now over here in this kind of a setting, you can see that you have two R's, there is one F. Okay, this is an F, that means there is a like a transform fault boundary over here, and this is a T, and this is also a T. T means subduction. Okay, so over here you have this R T R. Okay, now over here you can see that this plate is actually moving like this. Okay, this is moving like this. This is overriding it. Okay, and this is getting subducted. Soon what will happen is this entire plate might move like this only. It is going to keep moving like this, and over here somewhere here there will be another R. Okay, so whenever a plate is colliding somewhere, it is going to form a ridge at the other margin. Okay, usually this is the kind of the logic of how the plate tectonics are going on, like they are all moving. So this is another example of a Macquarie triple junction. So if you have RTR, if you see over here, if there is one of any of the examples over here, you can see whether it's a stable boundary or a stable triple junction or an unstable triple junction. Okay, so over here you have TTR A, TTR B. It will stay stable only if there is a condition which is met. Okay, now these are some of the features that we find across the earth. Okay. These are some of the features that are formed due to the plate tectonics that are playing a role on the earth. You have oceanic trenches, you get volcanoes, you get hotspots. Okay, I will go at for each feature. Okay, so first we talk about the convergent plate boundary, that is destructive plate boundary, that is where collisions happen. Okay, now convergent plate boundaries can happen at three different settings. One is between oceanic and continental, the other between oceanic crust, and the third one is continental crust. Okay, subduction, continental plate boundaries are where you have subduction zones. Okay, and it can happen between combinations of the crust. Okay, so you have oceanic continental crust, oceanic crust, and continental crust. This is kind of a cross section of a subduction zone. Okay, so this is a cross section. You can see that this is between an oceanic crust and a continental crust. Okay, you can see that the continental crust is moving towards the oceanic crust. Now, why is oceanic crust the one that is moving down? It's because it is denser. It is denser than the continental crust. So it is easier for the denser crust to move down into the mantle. Okay, this is where you will get your trench. Okay, and these when the oceanic crust is going down, okay, some of that material will kind of start melting here itself, and it will give rise to smaller volcanic arcs. Okay, because of the melted crustal material from the mantle, it is coming from the shallower part. Okay, it is rising towards a crust and you will get a volcanic arc. Okay, and then you have the accretionary wedge, and then you have the four-arc basin. These are some kind of features of a subduction zone. This is a generalized diagram. You mostly get these features, okay, at the subduction zones. There might be some differences in the spatial relationship of these features. Now we will see an example of the continental collision, okay, or the convergent plate boundary between two continents. Himalayan orogeny is between the Indian plate and the Eurasian plate. Okay, so both are continental landmass. Okay, and as we had spoken before that there was Tethys Ocean between the two plates. Okay, before the collision. Okay, so this ancient oceanic crust, this is the Tethys oceanic crust. Okay, this is the Eurasian plate, and the Indian plate was moving. Why? Okay, Chaitanya has asked, why is it so, ma'am, that the oceanic crust is denser, even though the rock material is same? That okay, most of the continental crust is not basaltic in nature. Okay, it is mostly sedimentary in nature, and if you understand the entire way of melting, okay, the mantle material rising, and because it is rising, it starts cooling also. Okay, when it starts rising, I'll just show. Okay, so this is your say crust. Okay, your mantle material is rising. Okay, and your depth increases. Okay, this is your 0, this is your z. When any mantle material starts rising, okay, it starts cooling. Okay, temperature is higher as we go down the depth. Okay, so the temperature decreases, the material starts cooling. Okay, so when anything that is in the molten state starts cooling, the material that has the highest melting point will start, cooling and crystallizing. Okay, now the basaltic material that we talk about, or the ultramafic material, where if we talk about rocks, okay, so these material have higher melting points, so they are the first ones to crystallize. Basalt basalt is made up of minerals which crystallize at higher temperatures. Okay, so when it starts melting, or when it starts cooling and coming up, the first material that will get crystallized out and out of the mantle material that is coming on top will be basalt. Okay, this is a generic example. This is much more complicated in real life situation, but just to make you understand why the density is different and how the continental crust is actually the last to form when the mantle material is rising. Okay, so when basalt is getting crystallized out and it is forming your oceanic crust. Okay, so less denser material is remaining in the molten mantle material. Okay, so as we know that less dense means it will still rise up towards the crust. Okay, so you can see that the denser material will start going out, over here, oceanic crust, as oceanic crust, as oceanic crust. What we are left with is the low density material that is forming your continental crust. Okay, so this is due to the what we call as differentiation. The mechanism that is happening here is the differentiation that is happening because denser material is getting crystallized out because the mantle material cools. If we take a sample of oceanic, it is more denser than the continental one. Yes, if you take an oceanic basalt and if you take a basalt that is found on the continent, you will find that the one that is in the ocean, first of all it will differ in composition. Okay, and the cumulative density, if you measure with proper laboratory processes, you will find that the oceanic crust one is denser than the one that is being found in the continent. Is that clear? It's mostly because of the chemical composition that starts, and the thing that I just explained is one of the mechanisms that denser material keeps cooling and crystallizing out of the mantle material. The mantle material which is rising up gets lighter. So maybe a lighter or less dense basalt will form on the continent. Okay, but that also it will not be because that will not be at the depth, right? At the depth you will only find the denser material only. And also one more thing to remember is ocean is where new crust is continuously being formed. Okay, even in ocean crust, like suppose you consider this is where your new material is coming up. Okay, as you go away from this area, this is actually a ridge. Okay, MOR, a mid oceanic ridge is where new mantle material is coming up, suppose. Okay, so even the oceanic crust which is closer to the the a place where the mantle is coming up, this is going to differ than the one which has become older now. So there will be some compositional difference even then, it will not be constant. So this is the reason why we say that the oceanic crust is denser than continental crust. Okay, so okay Chaitanya, hopefully you got that. Okay, so we were talking about the Himalayan orogeny. We can see that the Indian plate is was moving towards the north, okay, and the Eurasian plate was over here. You can see that the Indian plate, obviously now Indian plate is also continental plate, okay, and over here it is showing that it is kind of it collided. This ancient oceanic crust started, it became a part of the Himalayan orogeny. Okay, The tip of the Indian plate is where most of the deformation that, took place. These smaller arrows that you see, these are different thrust faults. Okay, these are different thrust faults. What is a thrust fault? In simpler terms, suppose this is a block of rock, okay, and you find like there's a kind of zone of weakness that is present over here. Okay, now if this rock, if this block, after some time there is deformation and there is displacement, okay, this rock moves on top and this block moves downwards, what you will get is like this. Okay, the block becomes like this has moved on top and this is going down. Okay, so this is called a thrust fault or a reverse fault. Thrust fault is when the angle of this surface is very low, okay, that is a thrust fault. Okay, so there are different thrust faults at the tip of the Indian plate. Okay, now after this is at the time of collision. Okay, now after the collision you can see that all of this ancient oceanic crust got hidden over here. Okay, and the tip of the Indian plate, is where the collision is still going on. Okay, the Eurasian plate is moving towards the southern side and the Indian plate is moving in the north side, and this is going on happening. Okay, so this is the reason, because this is an ongoing collision, you find active faults in Himalayan region, which is responsible for a lot of the earthquakes that we hear about that happen in the Himalayan region in Nepal. Okay, the recent, the most, yes, somebody raised a hand. Okay, maybe that was my mistake. Okay, so the most recent Nepal earthquake that happened, I think in 2015, was along one of these faults that are present in the Himalayan region. Okay, so over here that there are these different thrust faults. Okay, you have the main frontal fault, you have the main boundary fault, you have the main central fault. Okay, and the Himalayas are kind of classified into three different zones based on these faults. Also, you have sub Himalaya, lesser Himalaya, and higher Himalaya. Okay, you can see that this is the Indian basement that is still moving towards the Eurasian plate, and that Eurasian plate is still moving, in the southward direction. Okay, this is one of the examples of convergent plate boundaries. Now we come to oceanic trench. I think the most famous oceanic trench that you might have heard about is the Mariana Trench. Okay, it is also the place where you find the deepest point of the earth, that is the Challenger Deep, that is around 11,000 kilometers. Okay, so Mariana Trench is the deepest point on the earth, and in Himalaya you will find that it has the highest point of the earth. Okay, so both of these places, obviously like not related, but both of these are features of convergent plate boundaries. Because of these convergent plate boundaries, you find a feature on earth that is called the ring of fire. You might have heard about this. Okay, so ring of fire, wherever you have trenches, there will be a volcano associated with it. Yes, Bhargav, you have a question? Yes, Bhargav, do you have a question? I see you have raised a hand. If you have a question and you cannot, speak on the mic, then you can also type it in the chat box. Okay, I'll answer. So, wherever an oceanic trench is present, there will be an associated volcano also. Okay, so this entire place, that is the ring of fire, this is the area where you will find the most of the subduction zones. Okay, all these trenches are formed because of the presence of a subduction zone, and this is a ring of fire because there are volcanoes associated with these trenches that are present over here. Okay, So this is another cross section of where a trench is being formed. Okay, the overriding plate, the trench will be formed at this kind of a position. Okay. So now we come to divergent plate boundaries or constructive plate boundaries when new crustal material is getting formed. Okay, you can have two types of divergent plate boundary feature. One is your continental rift and one is your mid-oceanic ridge. Okay, African Rift Valley is one example, and also the mid-Atlantic Ocean ridge, okay, is an example of the mid-ocean ridge. You can see over here when the plates are moving away from each other, mantle material, okay, mantle material is rising on top, okay, and because the plates keep moving, okay, also the oceanic plates are moving, different kinds of mountains, kind of small hills or ridges as we call them, are getting formed along the plate boundaries, okay, along the margins. So rift system is where the kind of the plate boundaries are happening within continental system, okay, or it is forming a rift basin as we call them. Okay, over here you can see that the two blocks are moving away from each other, okay, and this area is actually the rift system. Okay, why is it called system? Because there are many more smaller such extensional features that are forming within the rift system. Okay, over here you can see the plate boundaries are these dotted lines. Okay, the developing plate boundary, like because of the building up of the crust over there or new material getting formed over there, you can see that a new plate boundary is getting developed over here. Okay, so this, when you consider that these two are actually the branches of the or the arms of the East African rift. Okay, and because see along these plate boundaries the plates are moving like this, and that is why you have the opening of the seas or opening of water bodies over here. Okay, so this is due to the convergent plate boundary. Mid-Atlantic Ocean ridge, as I said, is because of the convergent plate boundary existing between two oceanic plates, or maybe two continental plates which also has oceanic plates attached to those continental plates. Okay, you see that actually the MOR that is actually traversing across the entire of most of the Atlantic Ocean. Okay, and also within Iceland itself, Iceland is one islandic country. Okay, it's an island, but it the mid Atlantic Ocean ridge is actually traveling through Iceland over here. Okay, so the plate boundary is kind of going through one single island itself. So Iceland is actually breaking apart because of this. Now we come to the transform plate boundary. Okay, so you have two plates which are moving past each other. One of the most common example is your San Andreas fault. Okay, so the main fault is given in the purple, and these yellow ones are faults that have been formed due to the movement of the plates across this San Andreas fault. Okay, you can see over here the rocks are getting they are being moved past against each other. That's the only thing. And this, and because of the the movement along the plate boundaries, this entire region is going to stay deformed. This place is also one of the active seismic places. That means a lot of earthquakes happen here because of this movement of the plates against each other. Okay, another example of transform plate boundary you can see is between the Caribbean plate and the North American plate. You can see over here over here you can see the direction of the plates moving, and this region is a transform plate boundary. So this is how actually this is the transform plate boundary. Again you see over here, okay, there is a subduction zone here. That means actually the Juan de Fuca plate is actually subducting below the North American plate. Okay, soon this plate is going to get consumed beneath the North American plate. Okay, it's because of this move. This is why, you know, there were a lot more plates maybe in the past, okay, maybe smaller plates, okay, but quite a few of them got consumed because of the existence of these subduction zones. These plates got consumed because they were subducting below other plates. Okay. Now somebody asked me about, I think, how uh, Aravalli mountain ranges were formed. Okay, Aravalli mountain ranges are actually situated over here. Okay, now Aravalli mountain ranges is not a plate boundary. Okay, the mechanism of it is not a plate boundary, but it is formed due to the interaction of the Indian landmass with a different continental landmass. Okay, how does it affect? If suppose kind of, you know, any of the subduction or the divergence is happening at the plate boundary, because the mechanism is at such a magnitude, there are, you know, far off effects of these plate boundary processes which happens even in the interior. Okay, Aravalli mountains might have formed because Indian plate was supposed, you know, at certain point when it was getting rearranged in the geological past, when if you remember, I showed you all the different kind of reconstructions that researchers have did. At any point during that, you know, rearranging that was happening between the different continents, at a plate boundary between the Indian landmass and some other continent, because of say collision, you know, there might have been effects in the interior of the Indian landmass, and if there was, you know, is it transforming plate boundary right there at Trans Himalayas? Uh, no, there are no transform plate boundaries in Trans Himalayas. The entire Himalayan area is mostly built up of thrust faults, no transform fault. Okay. Yeah, it's probably the nomenclature of Trans Himalaya is related to something else. I am not aware of it. If I find it, I'll try to include it in the slides. Okay, later on. Okay, so Aravalli fold belt is actually most of it's actually a response to different stresses that Indian landmass experience because of some plate boundary process. It is not a plate boundary itself. Okay, who had asked this question? Pravesh. Yeah, are you still here, Pravesh? Hopefully that clears out. Aravalli fold mountains is not a part of the, yeah, it is formed by uplifting. Later on, if we are studying fold mountains or creation of fold mountains, we'll see that due to you know, compressional stress activities, a certain part of the, you know, landmass can get uplifted and form fold belts. Okay, Himalaya is also a fold belt, but it is part of a plate boundary process. Okay, so over here you can see that, you know, the plate boundary process is mostly related to the Himalayan orogeny. Okay, and also some part of this Myanmar belt also, where the Indian landmass is actually interacting with different plates per se, and all the tectonic regimes or the tectonic features that you find within the Indian landmass, they are mostly responses to different stress activities that you know, the Indian landmass has experienced during its geological evolution. Okay, as I said, I will give you some examples of you know, kind of how plate boundaries are, you know, present day consequences of the plate boundary processes. Over here we are going to talk about the Sumatra Andaman tsunami, which happened in 2004. It was one of the most devastating you know, disasters that had taken place. It's a natural disaster. Okay, so that happened because of the interaction between the Australian plate, the Indian plate, the Sunda plate, and also the smaller microplate of the Burma microplate. Okay, over here this is a simplistic diagram. You can see that, you know, this is an interplate thrust fault. This interplate thrust fault was coupled together with a transform plate boundary. Okay, this is the transform plate boundary. Okay, and this one was where your interplate thrusting happened. Okay, interplate disruptions can also cause earthquakes. Okay, it's not just earthquakes only occurring in the plate boundaries. Okay, interplate earthquakes also take place. So one of the example is this coupled decoupled faulting that happened for over here. Another example would be the Latur earthquake in Maharashtra. Okay, so these are examples of interplate earthquakes. Okay, so over here you can see that actually the earthquake that the movement that happened across the transform plate boundary gave rise to the interplate earthquake activity also. Okay, so right now currently these processes have happened on earth, like during its entire history, but right now it is important for us to know because it is causing risk to life and property. So it is important for us to know how understand plate tectonics and how it is affecting us, how it is affecting the earth processes also. Okay, over here you can see an animation of how the fault propagated northwards once it started over here. Okay, so the green is the transform fault boundary where it had happened, and because of this movement, the movement along this transform fault, you can see that this fault was also activated. Okay, so the red one is actually the uplifted part, and the blue part is where the there was a subsidence, the displacement happened. Okay. Now we come to the Turkey earthquake. Turkey earthquake again is actually the plate boundary processes are responsible for the occurrence of the Turkey earthquake, which right now is the one of the most devastating earthquakes that have happened in the current situations. So over here you can see, okay, these are some of the areas, okay, where seismic activities have been recorded. Okay, so first there was a 7.8 magnitude earthquake, then you had the 7.5 magnitude earthquake. Okay, over here you can see that both the earthquakes have happened along a fault. Okay, and even the previous earthquakes have happened along these fault regions only. Okay, so this fault is not a, you know, over here you can see that this fault is actually is actually existing between the Anatolian plate and the Arabian plate. Okay, so the 7.8 earthquake and the 7.5 magnitude earthquake, all of them have happened along these fault areas. So that is the East Anatolian fault. Okay, this is where the earthquake actually took place. So in the next slide we will see the kind of the movements of the different plates that are associated with the Turkey region. Okay, over here this is the fold and thrust belt. Over here you can see that Arabian plate is moving this side, okay, and the Anatolian plate is moving away from here. Okay, because of the movements over here, okay, over here the North Anatolian fault is meeting the East Anatolian fault in the Eurasian plate. Okay, all the plates while they are moving, okay, so the Turkey is somewhere over here. Okay, so actually Turkey, the plate that is containing Turkey is actually moving away from this area. Okay, this is a Dead Sea transform fault. These are the different kinds of faults and the different kinds of features that are present over. So the entire reason of the Turkey plate is because the tectonic processes, yes, strike slip faulting, transform fault. There is a strike slip faulting. It's because, okay, this is moving like this plate is moving like this, and this plate is moving like this. Okay. So and there is a transform fault here. Sorry, this will not move like this. This will move like this. It's not getting erased right now. Okay, fine. This will actually move like this, and this is moving because it's moving like this. Then this is actually moving like this. Okay. So these branches of the East Anatolian fault is also getting activated because of the tectonic processes over here, plate tectonic, plate boundary processes, and that is why this area is much seismically active. Okay. So actually the North Anatolian fault is meeting the Eurasian and the Anatolian tectonic plates. That part, actually the movement across along this plate boundary is actually very devastating, and because of any slight movement in this region is going to have effects in the weaker zones like uh, the East Anatolian fault zone. Okay. Now we come to the last. This is not related to any plate boundary movement, but it is actually the this shows us this hotspots. Okay, hotspots or volcanoes that are found in the ocean area. Okay, it is a giving us an indication that the ocean that the plates are actually moving. Why? Over here you see that right now this volcano is active. Okay, so you have an active volcano here, but if you find like a linear or a linear relationship between different other sea mounts, if you call them, you can suggest that this was actually where the first hotspot activity took place. Okay, then the plate moved, so the next sea mount was on top of the hotspot, the mantle plume or the hotspot area. Then as the tectonic plate moved again, then this was the one which was created, and because of this movement of the tectonic plate is this is the presence of this new hotspot is existing. Okay. Over here in the left side you can see that these are different. The red dots are the current hotspot places. Okay, current position of the hotspots, and the lines that are there is the actually the line drawn through the different chain of these sea volcanoes or ocean volcanoes. Okay, so these kind of lines actually show how the plates moved. Okay, so the plate was moving like this, then at some time over here there was a sudden shift in the direction of the plate moving. Okay, then it started moving like this. Okay, this is the orange lines represent the volcanic trail corresponding to each presently existing hotspot. This is the mechanism, okay, of how hotspot volcanoes are forming. You have a mantle plume that is rising through the mantle. Okay, it is coming towards the crust. Then if it is if suppose a continental suppose a continental part of the tectonic plate is on top of the mantle plume, you could have flood basalts. Deccan basalts is one example of such continental basalt which came into existence because of such hotspot activities. It was due to the presence of reunion hotspot. this hotspot below the Indian landmass. So, the reunion hotspot stayed at the same place, but the Indian plate moved across, okay, moved over this hotspot. And while it was moving over this hotspot, the area that is, encompassing the Deccan basalt, that area was on top of the hotspot for that entire period, because of which we got that we get a very large Deccan basaltic province. Okay. Otherwise, this is how a volcanic trail is formed. Okay, so this plate is moving this side. So this was the older one, this is the new one. Okay, this is constant over here. Mantle plume activity in a hotspot region, that is going to stay constant. Okay, but the plate is going to be moving over the hotspot, and that is why newer volcanic mounds are being formed. Okay, this is an example of the Hawaiian hotspot. First you had the Emperor Seamounts, then you had the Hawaiian Ridge, and then you had the now you have the Hawaiian Islands. Okay, so these are the present mounds or present Hawaiian Islands which are volcanically active right now. This is another example, that is the Yellowstone caldera. You might have heard about different geothermal systems that are present in Yellowstone. Okay, it is because of the existence of the hotspot in below the Yellowstone, which is giving the heat for the geothermal systems that are present over there. Okay, over here you can see the trajectory of the Yellowstone hotspot activity. So this it started say around 16 to 15 million years ago, and the current hotspot that is present below the Yellowstone, it actually happened at around 2 million years ago. Okay, obviously it is going to move again. Okay, because as we know, the plates are moving, the hotspot, the location of the hotspot on Earth's crust is also going to move. Okay, so these are some of the features of the plate tectonics. We learnt about the plate boundaries. Okay, different kinds of plate boundaries, how they are forming different features on the earth, how are they affecting us at the present day. Okay, so hopefully this was a good summary for the entire the week 3 content that you have, and hopefully that you understood the concepts, and if you had any doubts regarding the material or your assignment questions, hopefully this has solved those. If not, I will again put the YouTube channel link and the Google Slides link for you to refer back after the live session. Okay, so the NPTEL team probably is going to take a bit time to upload the recorded lectures or give you the YouTube link. So I have given you my YouTube channel link. So over there you can look for the playlist of the same as the course name, that is the Geomorphic Processes, Landscape and Landforms. So in that playlist you will find the previous week's content also, and this week's recorded lecture. Okay, so please go through the recorded lectures. If you have any doubts, you can post on the discussion forum, you can write in the comments. I will try to clarify the doubts over there or on the discussion forum. For now, if anybody has doubts now, can ask. Yes, Pravesh, you have raised your hand.
Yes, ma'am.
Yeah.
Ma'am, we didn't get the lecture PDF for week 4. Ma'am,
The
in
lecture
the
PDF is, but today it went live today, na, week 4.
yes, ma'am, but every week, ma'am, we get the lecture PDFs,
Yes, yes.
but ma'am, but for this week we did not get it.
Okay, I'll try to get in touch with the other teaching assistant and ask if there was some issue. Okay, and I'll try to get that clarified from them, and we will post it on the discussion forum. And otherwise, they can get in touch with the NPTEL team in case that has not happened. Okay.
Okay, yes, ma'am. Thank you.
Okay. Anybody else has any question? Yes, Yes, Kuldeep, you can share your screen.
Ma'am, I wanna ask you some.
Okay.
So we have this assignment, and ma'am, I wanna ask you this because
Okay, the dash is a layer of
Yes,
moist
ma'am. This
soil
question is from my side also.
followed by a zone in which open spaces in bedrocks are filled mainly with air. Okay, you remember I spoke about an zone of saturation and then zone of aeration.
water table. Yes, ma'am.
Yeah, so the Vado zone actually falls in that zone of aeration where you have many open spaces in the bedrocks as well as the sediments over there which is filled by air.
So the answer is Vado zone, ma'am.
Yes,
Right?
yes.
Okay, so ma'am, I have another.
Okay.
The third one, ma'am. Third one.
After dash million years, Phanerozoic eon starts, which corresponds to flourishing of flora and fauna on Earth. Okay, see, I cannot give you the direct answer, but if you go through the slides that I have showed, the geological time scale, okay, over there you can find the answer. Yeah,
Ma'am,
it is
here it
over here.
is. But ma'am, I think there should be before. I mean, here it is a word after, but I think it should be
Wait,
before.
let me
Before
take after dash million years.
because it's about past.
After dash million years, Phanerozoic. Yeah, I think there is a mistake in the.
Yeah,
Actually,
ma'am.
no, that is not kind of. I will try to see. Wait, let me see the thing. After dash million years, Phanerozoic eon starts. 2500 is Proterozoic. Yeah, I think it's the the kind of the sentence formation is wrong.
Oh,
Yeah, so it should be at dash million years, probably Phanerozoic area starts.
okay. So we will pick the C option. Okay, ma'am.
Uh, Phanerozoic eon. No, Phanerozoic eon is not C. I can only tell you that it's not C. So, if you try to go to the geological time scale, you will see where the Phanerozoic eon starts. Okay,
Okay,
it's an approximate number over here. It's given. Okay,
ma'am. I have these two more. Like
okay.
number eight.
Hmm.
So here it is the fourth option. All of these. So that is what making me confused.
What type of
Actually,
force is responsible for the
I
movement
think
of
the
rigid?
option C.
Yeah, I mean, I just discussed this in the session also. What is the driving force, which is actually, it is the responsible of for the tectonics.
Option C, right?
Yeah,
But there is another option that making me confused,
all
like
of
the
these.
fourth
No,
option.
no. See, gravitational force has no effect on the Earth's interior layers. It is
Oh,
only
okay.
effective on the surface of the Earth, na?
Okay, ma'am. So these were the questions I wanted to ask.
Okay. Anybody else has any doubt?
Thank you, ma'am.
No problem. Okay, so if anybody else has any doubts while going through the weekly content or during the if you are seeing the recorded lectures on YouTube, so please write them in the discussion forum and we will get back to you, either the teaching assistant or me. I will be mostly responsible for any doubts regarding the live sessions that are happening. Okay, so please, I would say subscribe to the YouTube channel. Ma'am, can you clear that? Okay, I'll just clear that once. Is my screen visible?
Yes, ma'am.
Okay. So over here, yeah. So over here you see the zone of aeration. Okay. The vadose zone is actually present in this layer where along with water, the spaces between the voids or between the sediments or the bedrocks is also filled with air. Okay, because it obviously it's closer to the surface, right? So there will be water as well as air. So this area is actually called zone of aeration. So vadose zone is a part of the zone of aeration. Okay, and zone of saturation, where you will see that there is only water that is percolated between the pores of the bed of the rock or all the of the sediments that are present over there. Did you understand?
Yes, ma'am. I get it.
Yeah. So the water actually trickles down through the zone of aeration and the zone of saturation, that could be an aquifer. Okay. The aquifer will get saturated and the layer above the aquifer which has air also in the pockets, because mostly the top layer is going to be your loose soil, loose sand. You will have some organic material also over there. Okay. So this is not compacted. Okay, this is very porous and very permeable, and because it is closer to the surface it will have your air also over there. Okay, that the vadose zone is part of this zone of aeration. Yeah, Kuldeep, what's your question?
Ma'am, I wanna ask you, like, the question was the same question. So, the Vadose zone is a layer of moist soil, followed by a zone in which open spaces in bedrocks are filled with mainly with air.
Yeah.
So, ma'am, Vadose zone is the zone where water and air both are available,
Yes.
and
Yes.
water table is a zone where only, I mean,
Yes.
every single pore
It's only
is
saturated
full.
with water.
Yeah, but ma'am, if Vadose zone is the right answer in that question that I asked you, so ma'am, why it is followed by a zone with the open spaces with air?
See, ekdam the top layer, okay, it will be more moist. Okay, maybe the layer below it is not that permeable, but it is porous and it is loose and it is very much it contains all different kinds of material.
Hmm.
Do you understand that?
Um,
I don't have a figure right now. I'll just see.
Ma'am, I know about water table. The below of water table there is saturation zone. Um,
I'll just like Google here. Okay,
yeah.
as I even showed, even the diagram that I was showing in my in
Yes,
my
ma'am.
slides also, the
Yeah.
region above, okay, is
Hmm.
the zone of
That is.
aeration. Aeration, why? Because it has both air and water in it, and that itself is called the vadose zone. Okay.
Hmm. Yes, ma'am.
Why is it moist? Because the water is trickling down this zone, right? It is going to trickle down. It is not getting saturated because the
There
the
is.
pore size, probably the number of pores, or the porosity is very high. Okay, it has voids. Anything that is not getting confined has a lot of air voids also. Okay, so if you go with the question, so the vadose zone is the moist soil layer, okay, through which the water is flowing down, and there is also a layer which is filled with air also over there. The construction of the question is in a very general manner, but the vadose zone would be the almost the entire portion above the water table.
Okay, ma'am. But actually, ma'am, that is saying Vado zone is a zone that is followed by a zone with
Hmm.
open spaces with air and water. If that is saturation zone, then there will be no air. There will be only water.
No, no, vadose zone is in the unsaturated zone. The end over here in the simplistic diagram, they are showing the entire thing as vadose zone, but vadose zone is part of that unsaturated zone. It's not the entire zone.
Okay.
Okay, some places you will have the thick vadose zone as you can see over here. Okay, and some places you will have thinner vadose zone. That means the aquifer over here, obviously this is an example of how vegetation also plays a role in the recharge of groundwater, but we are not looking at that. We can see that it can be a thin vadose zone, it can be a thicker vadose zone also. Okay, so in the thicker vadose zone, are you going to say that your the entire portion is going to be saturated with water as well as air? Do you understand? Did you understand? I think the entire question, the meaning of the question is whether the vadose zone only contains water or it contains both air and water. I think that was the perspective with which the question was asked. Maybe the framing was a bit different, okay, but the general idea is that the vadose zone is an unsaturated zone. It has both air and water, okay, in between the
Ma'am,
pore spaces.
uh, actually, I have understand the difference between Vado zone and water table saturation zone. But the question is asking like a zone. Vado zone is a zone which is followed by a zone with the air, because if there is air then it will be weather zone. If there is only water then it will be saturation zone.
See, that is
So
what I'm saying. The point of the question was to make you understand that vadose zone consists of both water and
and
air.
air.
Okay,
Yes.
the framing of the question might have been different. Okay, I am not in charge of making the questions.
uh,
So maybe the framing of it was a bit different, but the context of the question was to ask you which is the zone that has both air and water. That is the zone that is above the water table.
hmm. By the way, ma'am, I can defer them, and uh, I can show you one more time the question.
Yeah,
uh,
I saw the question. I understood the confusion that you have.
can I show?
Yeah,
Okay, ma'am, just a minute.
yeah,
So ma'am, this is the question.
yes.
This is the only question that is wrong.
Yes, I can understand that why you're getting confused. The dash is a layer of moist soil followed by a zone in which open spaces and bedrocks are filled mainly with air. Okay, so what did you answer? You said none of these.
Yeah, ma'am.
Okay, that entire
Because
zone of
moist soil.
aeration that I talked about, okay, that is vadose zone. So you
Hmm.
just have to remember that vadose zone has both air
Air and water.
and water.
Hmm.
Okay,
Yeah.
that's why I'm
Yeah,
saying the
ma'am.
framing of the question is a bit confusing probably for you. Okay, now see, uh, saturated zone
Yes,
does
ma'am.
not have air.
Yeah.
Okay,
Only water is there in the
water table is
yeah, ma'am.
uh, the the uh, mm, the
The
line
below water
or the
level.
level. Okay, beyond which it there is aquifer,
Only water.
yeah, only
Yeah.
water in the pore spaces. Okay, vadose
Mm.
zone is one of the layers probably, if you like, as per the diagrams that have been given in your content and as well as the one that I gave. Okay, vadose zone is found above the water table, है ना?
Yeah, above the water table.
Huh,
Yeah.
so that is the option which is closest to your question, like the answer.
Mhm. Okay, ma'am.
Yeah. So it is a bit confusing. The question might be confusing, but the context of it is this, that vadose zone is the layer where you will find both air and water in the pore spaces.
Okay, ma'am.
Okay.
Okay, ma'am.
Okay. Any other question?
No, ma'am.
Okay.
Actually, I will have when I will solve the next assignment.
Yes, yes, sure. So every week we will have this. So you will go through the week 4 lecture that is live now. So in next Friday, I will deal with the week 4 content. So you go through
Actually,
the week 4
ma'am,
content. Any doubts that you have from that assignment, you ask me.
ma'am,
Yes.
in the week 4, we did not get any lecture
Yes,
PDF.
yes. Already Pravesh has informed me of that. I will try to get in touch with the TA that is,
Mm.
handling the NPTEL course, the content and everything. So I will try to get in touch with him to see if there's an issue, and he'll get in touch with the NPTEL team, and hopefully wait till tomorrow or day after. Maybe the week 4 lecture PDFs will be given by that time.
Okay, ma'am.
Okay. Anything else?
No.
Okay.
Thank you, ma'am.
Thank you so much. Thank you for coming for the lecture, interacting with me, getting your doubts cleared, and hopefully it was helpful. Okay, so for now, or for today, this is all. And I hopefully I'll see you in the next week's live session. That will be Friday, next week Friday.
Yeah, ma'am. We are glad that you can cover, uh, I mean, in detail every single thing that I have gone through, and that is even more in detail. And you are uh, explaining us so easily.
Thank you so much. That is what we, as a PhD scholar, I'm really glad to hear that my explanation, I can get it across to you and you all can understand. Yes, thank you so much for all the kind feedback and responses that all have given me, and hopefully these will be helpful in the upcoming weeks also. And please refer to them in the YouTube channel that I have given, so you can get all your doubts cleared again if you have missed anything or you've missed a part of the live session. Okay, so that's it for today. Thank you. See you next week.